Welcome to this video beginning chapter 11 in our geometry class, Transformations and Orientations. This is a short chapter. Hopefully you'll enjoy it. A lot of pictures. So if you take your class notes out and your definitions. First let's start with the definitions. We have quite a few about transformations. What is a transformation? A transformation is a change in the position, size, or shape of a figure. Each point of the original figure, called the pre-image, gets mapped to a unique point in the new figure called the image. So pre-image and image. So it begins as a pre-image. You can think of pre as before it gets moved or changed in some way. And then the image is after it's been moved. Isometry is a transformation for which the image is always congruent to the pre-image. And the majority of transformations we'll see in this chapter are isometric, the adjective. Isometric meaning it's congruent to itself. The only way it wouldn't be congruent to itself is if it changed size or shape. If it got bigger than it was, it's not congruent. It's similar but not congruent. If it changes shape, if it changed from like a triangle to a square or something, that's not congruent to itself. There's two types of orientation, opposite or reverse orientation. Two congruent polygons have opposite orientation if their corresponding vertices are ordered in the opposite direction. So notice if you go alphabetically, you have A, B, C, kind of going counterclockwise. Reverse orientation, now A prime, B prime, C prime. You're going in the opposite direction, the reverse direction. As I mentioned before, A and A prime correspond to each other. And the A prime is pretty handy, so you don't have to figure out if they were using WXZ, you don't have to figure out which one goes to which. So it's pretty nice. The other type of orientation is same orientation. Two congruent polygons have the same orientation if their corresponding vertices are ordered in the same direction. So a similar example, you have A, B, C. Going around counterclockwise. Here's A prime, B prime, C prime, going around counterclockwise. So they are ordered in the same direction. One type of transformation, a change in the position, transformation, is a reflection. A reflection is a transformation that maps each point to its mirror image across a fixed line. A reflection is also called a mirror reflection or flip. So here's your reflection line, and getting the mirror image of this arrow right here, we'll put the arrow over here. So that's a reflection. Notice this is an example of isometry. The arrow has the same shape and size. It's congruent to itself. It's just been reoriented. A translation is another type of transformation. A translation of the plane is a transformation that moves all points the same distance in the same direction. So same distance in the same direction. Well, we were talking about a word called vector, which is about distance and direction. So a translation moves all points in the same distance, same direction. The arrow that indicates the distance and direction of the translation is called the vector of the translation. A translation might also be called a glide. You can kind of imagine the arrow gliding to a different position. This is another example of isometry. The arrow is the same shape and size. It's congruent to itself. It's just changed positions. So each one of these points, each one of those points on the arrow has moved. This might be a little more difficult to show, but every point has moved. And you can see those blue lines compared to the dashed line. They're parallel. They're the same direction, and then they're the same distance as well. If we were to actually measure each of these arrows, it's the same distance. So far we have a reflection and a translation as two possible transformations, how we can transform the picture diagram that we have. Another type of transformation is called a rotation. Rotation is a transformation that moves every point the same number of degrees, about a point of rotation, a fixed point of rotation. So if we're rotating this arrow, this would be clockwise. Rotating this clockwise a certain amount of degrees, maybe 80 degrees degrees or so, then we get the shape up top. So this is our pre-image, and then this is the image. So pre-image is before the transformation. A rotation of 180 degrees is a half turn. Half turn, rotation of 180 degrees, should make sense. Anytime people talk about conversion and they say, I made a complete 360 degree turnaround, it really aggravates me. You'd be right back to where you started. So if you ever share about someone doing something in your life that you turn 180 degrees, use 180, not 360. A glide reflection is a combination of two. A glide reflection is a composition of a glide, or translation, followed by a reflection in a line parallel to the translation vector. So translation vector is this line right here. It moves it a certain distance and a certain degree. And then you flip number 2 over this reflection line, and then you get number 3 up here. So that's a combination of two. We won't deal with that too much in this chapter. As for theorems, properties of reflection, translation, and rotation. A reflection is isometry. The image is mapped onto a congruent image. A reflection reverses orientation. So that should make sense. If you have a shape like this and you're reflecting it, that should be isometric, the same shape and size. If you had ABC here and you go, this is clockwise ABC. If you reflect over the line, A prime, B prime, C prime, then the letters go the opposite direction. So they reverse orientation. And the line of reflection is the perpendicular bisector of the segment joining any point. So if you think of these 2 points being joined, this line is the perpendicular bisector. So it's not only perpendicular, but it also bisects the line. Properties of translation. Translation is an isometry. So it's congruent images. One is mapped to the other. A translation does not change orientation. So if we have this triangle, and we're moving it up here, and you have ABC, you have A prime, B prime, C prime. The orientation is not changed. It's the same orientation. And the shapes are congruent, which means it's an isometry. Properties of a rotation. Rotation is an isometry. Rotation does not change orientation. A point and its image are the same distance from the point of rotation. So if we have ABC, and we have A prime, B prime, C prime, try to make them congruent. Notice the rotation does not change the orientation. You have ABC going clockwise, and you have A prime, B prime, C prime going clockwise. And each point and its image are the same distance from the point of rotation. So if my point of rotation of here, C and C prime, are the same distance away from the point of rotation. Property of a half turn. Under a half turn, the center of rotation is the midpoint between any point and its image, which should make sense if you are, if this is your image, and this is your pre-image, and this is your rotation, point of rotation, then these 2 lines are congruent. And for theorem number 5, properties of a composition of reflections. This is for the very last lesson, but I'll read it to you now. Composition of reflections in 2 parallel lines is a translation. Composition of 2 reflections in 2 parallel lines is a translation. So let's say you have this shape, ABC. You're reflecting it over this line. So you'd have B prime at the top still. You'd have C prime here and A prime here. Now let's say you reflect it again. If you reflect this again, you'd have A, I guess you'd say double prime, C double prime, B double prime. And notice if you're comparing the original with the final image, notice that this is equivalent to a translation, which is what this theorem says. If you do two reflections in parallel lines, then it's a translation. That only works if the lines are parallel. Obviously, if you chose to reflect the second one over this line, then the A would be down here and the C would be down here, and that would not be a translation. But that might be a rotation, which leads to the next one. A composition of reflections in two intersecting lines is a rotation about a point of intersection of the two lines. So let's actually draw that. We'll get rid of this one for now. You can leave it on your paper. And let's say that we reflect over this line, and then we reflect over this line. They don't have to be perpendicular, just intersecting lines. If you reflect this now, you'd have this shape. So this is A double prime. You'd have C double prime. Down here you'd have B double prime. So notice this is not a translation because the orientation is changed. But the orientation is changed as a rotation would. So notice you have ABC, which is clockwise, and you have ABC around that direction, which is clockwise. You can kind of tell, well, at least my diagram isn't very good, but the point of rotation is right about there. I should have drawn my line a little higher. The point of rotation is right there. So composition of reflections in two intersecting lines is a rotation about a point of the two lines. Okay, that was quite a few definitions and theorems. So let's actually look at these examples. Was the image obtained by reflection, rotation, or translation? You're going to be asked that for the next 4. So how about you see if you could pick, is it a reflection, a rotation, or translation? See if you can intuitively figure it out. So pause this video. Okay, looking at the first one, looks like this tomato right here compared to this tomato right here. If we turn this tomato, this one's going to be on the side down here. This one will be right up in front. So it looks like it's a rotation or a turn. Was the image obtained by reflection, rotation, or translation? Well, if you notice maybe these points right here, they're in the exact same spot, as well as every other point is translated, or it has slided. So that would be a translation. For this image, this half is on the left side now, it was on the right side, so that would be a reflection about a line, or a flip about a line. Number 4 is interesting. I hope there was a massive debate and discussion about number 4. Now, my first thought is, well, it's a reflection. Here's the line that you can reflect the T or the cross. But it looks like it's also a rotation. If you take this side and you rotate it, looks like 180 degrees, that would also work. So it's actually both. Is it a translation? No, it's not a translation. Translation, this part of the cross is always going to be on the left for a translation, and it's reflected or been rotated to the other side. So it's not a translation. I mentioned this before. To help us match an image to its pre-image properly, we use letters with primes. So what type of transformation is this? It's not a translation, and it's not a rotation, it's a reflection. But the main idea is all the primes, which I mentioned before, and that's, there's an extra A right there, you can get rid of that. On to the next page. Practice with primes. Write the second letter of the second figure to illustrate the image as a reflection. Reflection. So if it's a reflection, it'll be reflecting over this line. The line should be halfway in between, in the middle of the two. Reflection over that line. So the B is going to be on this side, B prime. C prime will be up here, A prime's down here, and D prime's right here. See if you could do the next one as a rotation. So pause this video and take about, 5 seconds. See if you can label those. So the answer you should get for a rotation, this point's still going to be B prime, this is going to be D prime, but the difference between the one above is now C prime's down here and A prime's up at the top. So that's the main difference between the two. Look at the apple above. Which of the following figures have the same orientation? So if I were thinking through this, I would probably rotate this 180 degrees, and I would have the leaf, if you can imagine that's a leaf. There's the apple. The leaf would be on the right, so looking at this, the leaf is on the left, so that wouldn't be the same orientation. This one has a leaf on the right, this one has a leaf on the right, this one has a leaf on the left if you turn it. So all kind of different rotations. On this one I do the same thing. So you have this, maybe this small one right here, or this little branch going out on the left. So looking at this, the branch is on the right. Looking at this one, it's on the right. Looking at this one's on the left. Looking at this one, if you rotate it this way, it would be on the left. So those have the same orientation. For page 3, that's a different video that you're going to watch. And for page 4, that's a different video that you're going to watch. So let's finish with page 5, and then we'll go back and watch some videos to show how to do those other points. So vectors and translations. On a coordinate system, a vector is described in terms of the horizontal and vertical change when going from its tail to its head. The horizontal and vertical change are written as an ordered pair. Do not confuse this with the coordinates of a point. So rather than parentheses, we use these kind of pointed brackets for vectors. So the vector positive 2 comma negative 4 is the vector. This means translate every point horizontally 2 units. So the first number you see still corresponds to the x-axis. So 2 units to the right, it's positive, so it's to the right. If it's negative, it's to the left. Vertically, 4 units down. So the second number in the ordered pair still corresponds to the y-coordinate, the y-axis. And it's negative, so you go 4 units down. So to draw the translation of the polygon on the coordinate system, let 2, negative 4 be the vector. So here's our shape. We're going to move every point 2 to the right and 4 down. So really just do the vertices. So if we're looking at this vertice touching the axis, we have to go 2 to the right and 4 down. So that would be this point right here, negative 1, negative 4. And this point, we go to the right 2, count 2, now you're on the axis, and go down 4, so you're at this point. And the very top one, you go over 2 and down 4, looks like you're right here. And this one on the top right, you go over 2, down 4. This is, remember, translations are isometric, which means it should be congruent, same shape and size, same orientation. And that would be your graph with the vector. Why don't you pause this video and see if you could do the next one. Welcome back. This is the answer you should get. You go to the left 3, and you go down 5. Next we have name the vector of translation. So let's draw in the vector. You need to know where to start and where to end. The pre-image is where you start, the image is where you end. So let's pick a point right here. It is mapped to this point, and our vector is this line. So to write the vector, you're going to have those pointed parenthesis-looking things. We have, how much did we go left or right? Well, we went 6 to the right. And you might be asking, well, you could look at it the other way. You went 6 to the left. But you have to start at the pre-image. So the pre-image is where you start. And then you can see how much did we go up or down. From this point, we went 1 up. So your vector would be 6, 1. See if you could do the next vector. Pause this video. Here's the answer you should have. You could pick any point. I chose to pick the top point. It's the easiest if you pick a vertex rather than a point on the segment, not an endpoint. So pick a vertex and you go 6 to the left and then you go 5 up. Again, remember to start at the pre-image. If you had 6, -5, you started at the image. So it should be -6, +5. Last 2 questions. The next page is on a different video. Last 2 questions. Name the reflection of 2, -4 when reflected about the x-axis. So what this means, here's the x-axis, and if you had the point 2, -4, and if you're reflecting it over the x-axis, you would be down here. So notice the x-coordinate stays the same for reflection over the x-axis, but the y changes. So I didn't do that very well, did I? The point should be under the axis to -4. And when it's reflected down, it's above the axis. That would make a lot more sense. Sorry about that. Get rid of that. So this is the x-axis. The point starts below the axis. Name the reflection of -3, 5 when reflected about the y-axis. Here's the y-axis. -3, 5. -3 is on the left of the axis, so -3, 5 somewhere over here. Notice it doesn't matter too much about doing the axes and graphing the, going left 3, up 5, because you're reflecting it about the y-axis, so you're over here somewhere. And see if you can name those coordinates. I'll give you 4 seconds. If you got 3, 5, you deserve a pat on the back, so pat yourself on the back. Thank you for watching this video. You have a few other videos, I think 3 other videos about, maybe 4 other videos, about drawing these different types of transformations. Thank you.